Look down at the ground beneath your feet. Somewhere under that floor, under the soil, under the rock, there is stone that has never seen sunlight. Stone that has been sitting in darkness since before there were oceans. Since before there was air you could breathe. Since before there was anything alive on this planet at all. And if you could travel back far enough, 4.5 billion years, and stand in this exact spot, you would not survive 1 second. There is no ground here. There is no sky. There is a world of liquid rock, glowing orange and red. Oceans of molten stone stretching to a horizon that shimmers with heat. The temperature is over 1,000 degrees. The air, if you can call it air, is steam and carbon dioxide and sulfur. Rocks the size of cities are falling from the darkness above, every hour, every day, for millions of years. This is Earth, your planet, your home. This is what it looked like when it was young. And the question I want to answer in this video is simple, but it is one of the biggest questions in all of science. How did that ball of fire become this? How did molten rock become oceans? Where did the water come from? Where did the moon come from? Why does Earth have layers, a core, a magnetic field, seasons, tides? And why, out of everything we have ever looked at in the universe, did life happen here? Because none of it was guaranteed. Every step in this story could have gone differently. And if even a few of them had, you would not be here to watch this. So let's go back. Not to the beginning of life, not to the beginning of Earth. Let's go back further than that, to a time when there was no sun, no planets, no solar system at all. 4.6 billion years ago, this part of the galaxy was empty. No sun, no Earth, no Mars, no Jupiter, no moon. Nothing that you could stand on, nothing that gave off light. Just cold, quiet, enormous darkness. But it was not completely empty. Drifting through that darkness was a cloud so large that light would take years to cross it. Made mostly of hydrogen and helium, the two simplest, oldest elements in the universe, mixed with dust, tiny grains of carbon, silicon, iron, and ice. Grains smaller than smoke particles, spread so thin that if you were standing inside this cloud, you would not even notice it was there. Astronomers call this the solar nebula. Our nebula, the raw material of everything that would come next. Understand what that means. Every atom in your body was in that cloud. The iron in your blood, the calcium in your bones, the oxygen in the breath you're taking right now. It was all floating in the dark, going nowhere, doing nothing, for millions of years. And it might have stayed that way forever. A cloud like this is in balance. Gravity pulls it inward, trying to collapse it, but the gas pressure inside pushes back outward. As long as those two forces stay matched, nothing happens. The cloud just drifts, cold, stable, dead. Something had to break that balance, something had to push, and somewhere near our cloud, a star was dying. Stars do not live forever. A massive star burns through its fuel in only a few million years, and when the fuel runs out, gravity wins. The core collapses in less than a second, and the star tears itself apart in the most violent event in the modern universe. A supernova. For a few weeks, that one exploding star shone brighter than 100 billion other stars combined, and it threw its shockwave outward across space at thousands of kilometers per second. That shockwave reached our quiet cloud, and everything changed. When the shockwave hit, it compressed parts of the nebula. Some regions became slightly denser than others, and density is everything, because in space, density means gravity. Those dense patches started pulling in the gas around them, and as they pulled in more gas, they became denser still, which made their gravity stronger, which pulled in more gas. This is a runaway process. Once it starts, it does not stop. The cloud began collapsing inward on itself. And here is where something beautiful happens. Something you have felt yourself without realizing it. The cloud was already rotating, very slowly, almost imperceptibly. But as it collapsed, that rotation sped up. Think of a figure skater spinning with their arms stretched out. When they pull their arms in, they spin faster. They did not push off the ice again. They just changed their shape. Physics calls this the conservation of angular momentum, and it applies to a skater and to a cloud of gas the size of a solar system in exactly the same way. So our nebula collapsed, and as it collapsed, it spun. Faster and faster. And a spinning, collapsing cloud does not stay a ball. It flattens. The material at the poles fell straight inward, with nothing to hold it up. But the material at the equator was moving too fast to fall in. It was in orbit. So the cloud stretched out sideways and squashed down flat, until it became a disk. A vast, glowing, rotating disk of gas and dust, thousands of times wider than it was thick. We call it the protoplanetary disk. Proto means before. This is the disk that existed before the planets. And this one detail, this flattening, explains something you can verify tonight. Go outside. Find Venus, Mars, Jupiter, Saturn. You will notice they are never scattered randomly across the sky. They always sit along the same narrow line, the same path the sun and moon follow. Every planet in our solar system orbits on almost the same flat plane. That is not a coincidence. That is a 4.5 billion-year-old memory. The planets are flat in their orbits because the cloud they formed from was flat. Meanwhile, at the center of that disk, something enormous was happening. Gravity kept dragging material inward, and all that material piling up in one place meant pressure, and pressure means heat. The center of the disk grew hotter and denser and hotter still. It began to glow, dull red, then orange, then white. It was not a star yet. It was a protostar. A star waiting to be born, glowing only from the heat of its own compression. It needed one more thing. At the center of the protostar, hydrogen atoms were being crushed together harder and harder. The temperature climbed. 100,000 degrees, 1 million, 5 million. Hydrogen nuclei carry positive charge, and positive charges repel each other. Two hydrogen nuclei will do almost anything to avoid touching, but push them hard enough, fast enough, hot enough, and they cannot escape. At roughly 15 million degrees Celsius, they touch, and nuclear fusion begins. Hydrogen begins fusing into helium, and in that process, a tiny fraction of the mass, less than 1%, is converted directly into energy. The actual chain of reactions is complicated, but the outcome is simple, and it is the most important fact in your life. The sun switched on. Light poured outward for the first time. Real light, produced by the star itself, not just leftover heat. It flooded the disk. It lit up the dust. After millions of years of darkness, this corner of the galaxy had a sun, and that light has never stopped. The sunlight warming your skin today was made by the same reaction that ignited 4.5 billion years ago. Every plant that has ever grown, every meal you have ever eaten, every drop of rain that has ever fallen, all of it traces back to that moment of ignition. The newborn sun did something else too. It ate. It kept pulling material inward, taking the overwhelming majority of everything in the entire nebula. And that is why, even today, the sun contains about 99.8% of all the mass in the solar system. Let that number sit for a moment. 99.8%. Which means everything else, all 8 planets, hundreds of moons, thousands of comets, millions of asteroids, every rock and grain of dust from Mercury to the edge of the Kuiper Belt. All of it is made from the leftover 0.2%, the scraps, the crumbs the sun did not manage to swallow. Earth is a crumb. You are living on a rounding error, and the new sun also began pushing. A fierce solar wind blew outward from the young star, sweeping the lightest gases away from the inner disk. Hydrogen, helium, and ice were driven out to the cold outer regions. What was left close to the sun was heavier stuff, metals and rock, the material that could survive the heat. This one act of sorting decided the shape of our entire solar system. Rocky worlds close in, gas and ice giants far out. Mercury, Venus, Earth, Mars made from metal and stone. Jupiter, Saturn, Uranus, Neptune built out of the gas that got blown away. Earth is a rocky planet because it formed on the hot side of that line. Now we come to the part I find genuinely difficult to believe, even though we can watch it happening. How do you get from dust to a planet? Because a dust grain has essentially no gravity. 2 specks of dust floating next to each other do not attract one another in any meaningful way. So how does a cloud of specks become a world 8,000 kilometers wide? It starts with something almost embarrassingly ordinary: static. In the rotating disk, dust grains were constantly bumping into each other at low speeds, and when they touched, they stuck, held by static electricity and simple chemical bonding forces. The same reason dust clumps together under your bed. The same reason a balloon sticks to a wall after you rub it on your hair. Astronomers have actually observed this in other young star systems. In just a few thousand years, microscopic grains grow into clumps around a centimeter across. Small, fragile, nothing special. But the disk gives it time, and it gives it material. Centimeters become meters. Meters become hundreds of meters. And once an object reaches a kilometer or so across, something crucial changes. Now it has real gravity of its own. Now it does not have to wait for things to bump into it, it can pull them in. These kilometer-sized bodies are called planetesimals, baby planets, and there were billions of them. From here, it becomes a demolition derby on a cosmic scale. Planetesimals crossed each other's paths, collided, shattered, merged. The bigger ones grew fastest, because bigger gravity means a wider reach. The rich got richer. When a body grew to roughly the size of our moon, we call it a protoplanet, and these collisions were not gentle. Two moon-sized bodies meeting at several kilometers per second release energy on a scale that is hard to picture. The kinetic energy converts instantly into heat. Rock does not just crack, it melts, it vaporizes. Every major impact left the surviving body glowing, molten, seething with liquid stone. The whole process of building up like this has a name: accretion. The formal definition is the coming together and cohesion of matter under the influence of gravitation to form larger bodies. And here is a small piece of scientific history that deserves to be remembered. This model of accretion was worked out by a Soviet astronomer named Viktor Safronov, and he published it in 1969. Almost nobody listened. His work sat quietly for 15 years. It was only around 1984 that the scientific community properly picked it up, tested it, and realized that this man had essentially explained how planets are built. Today, his model underlies almost everything we understand about planet formation, and most people who love astronomy have never heard his name. Science is not always a story of instant recognition. Sometimes it is a story of being right too early. Now, a fair question. All of this happened 4.5 billion years ago. Nobody was there. No cameras, no records, no witnesses. So how do we know any of it? We know it 4 different ways, and they all agree with each other. That agreement is the whole point. First, we watch it happening elsewhere. Our telescopes, especially ALMA and the James Webb Space Telescope, can see young stars right now, today, surrounded by protoplanetary disks. We can see the gaps carved into those disks by planets that are still forming. We are not guessing at the process. We are watching other solar systems go through it while we take notes. Second, rocks fall out of the sky and tell us. Meteorites are not just space debris. Some of them are unchanged leftovers from the birth of the solar system, material that never got absorbed into a planet and therefore never got cooked, melted, or recycled. Cut one open and you find chondrules, small, round grains of rock that formed before the planets existed. They are literally the building blocks, frozen in place, delivered to your doorstep. And they contain radioactive elements, uranium, hafnium, and others. Radioactive elements decay at a fixed, unchangeable rate, which makes them clocks. Measure how much of the parent element is left and how much has decayed, and you can calculate an age. Do this on many meteorites, and you keep getting the same answer, about 4.56 billion years. That number is where the age of the solar system comes from. Here is a detail that makes me stop every time. Some of the uranium found on Earth is older than the solar system itself, around 6 billion years old. It could not have formed here. It was made in the death of some other star, in a supernova, long before our sun existed, and then it drifted through space and ended up inside our planet. Parts of Earth are inherited from dead stars. Third, comparative planetology. We can look at Mercury, Venus, Mars, the Moon, and the asteroids and compare them to Earth. Mars is small and its geology froze early, so it preserves an ancient surface. The Moon has no weather, so its craters have not eroded in billions of years. These worlds are archives. Earth erased its own early record through plate tectonics and erosion, so we read the record on the neighbors instead. And fourth, simulations. We take everything we know, the composition of the disk, the physics of gravity, collision speeds, cooling rates, feed it into supercomputers, and let it run. Then we check whether the simulation produces a solar system that looks like ours. It does. 4 completely independent lines of evidence: observation, chemistry, comparison, and simulation. If any one of them disagreed, we would have a problem. They don't. They point at the same story. So Earth grows. Collision after collision, over tens of millions of years. A protoplanet becomes a planet. Gravity pulls it into a sphere, because in a body that massive, gravity pulls equally in every direction, and a sphere is the only stable shape. And the world it produces is a nightmare. Geologists call this first chapter of Earth's history the Hadean Eon. It lasted from about 4.6 billion years ago to 4 billion years ago. 600 million years. The name comes from Hades, the Greek god of the underworld. They did not choose that name for style. They chose it because it is accurate. There is no solid crust for much of it. The surface is a global ocean of magma. Objects up to 100, 200 kilometers across are still slamming into the planet. Each one delivers enough energy to remelt whatever had begun to cool. The sky is dark with dust and vapor. There is no oxygen. There is no life. There is nothing here that would recognize you or that you would recognize. If a photograph existed of Earth during the Hadean, you would not identify it as Earth. You would think you were looking at a star. And now the twist that I love about this entire story, this hellish, violent, apparently pointless bombardment is the reason you have water to drink. Because not everything hitting Earth was dry rock. Out beyond a certain distance from the sun, past what astronomers call the frost line, water could survive as ice. The nebula contained ice crystals in enormous quantities. Comets and certain asteroids formed out there, carrying water locked inside them, and gravity threw them inward. Every icy body that struck the young Earth delivered its water as vapor. That vapor joined the thick, hot atmosphere. The bombardment that was tearing the surface apart was, at the same time, stocking the planet with the raw material for oceans. Some of Earth's water was likely here from the start too, trapped inside the minerals the planet was built from. When scientists analyzed the oldest surviving crystals from this era, tiny zircon grains, some over 4 billion years old, they find chemical signatures suggesting liquid water was present far earlier than anyone once believed. So the picture is, some water came with us, and a great deal was delivered. Either way, the sequence is the same. Water arrives, heat turns it to steam, steam rises. And eventually, when the surface cools even slightly, that steam falls back as rain. Rain on a world of lava, falling, evaporating instantly, rising, falling again. A cycle that would run for millions of years before the ground was cool enough for a single drop to survive. But it started here, in hell. By the end of the Hadean, Earth was essentially one enormous ball of molten rock held together by gravity. Everything mixed together. Iron, nickel, silicon, oxygen, aluminium, uranium, all stirred into the same magma. That is not stable. And what happened next gave Earth its structure. In a liquid, dense things sink and light things rise. Oil floats on water. Sand settles to the bottom. Earth was liquid, so Earth did exactly the same thing. On a planetary scale, the heaviest elements, iron and nickel, began sinking. Not quickly, not dramatically, just relentlessly, dragged down by gravity, filtering through the magma the way water works its way down through sand. Over millions of years, they gathered at the center and formed a core. Meanwhile, the lighter elements floated upward. Silicon, oxygen, aluminium, sodium, calcium, potassium, they rose toward the surface, cooled, there, and hardened into the first crust. This sorting process is called differentiation. It is the reason Earth is not a uniform rock. It is why we have a core, a mantle, and a crust. Let's go through them properly. The core, Earth's core, reaches roughly 6,000 degrees Celsius, as hot as the surface of the sun. At that temperature, iron should be liquid, and in the outer core, it is. But the inner core is solid, not because it is cooler, but because it is crushed. The pressure at Earth's center is over 3 million times atmospheric pressure, and that pressure forces the iron and nickel atoms into a solid lattice they cannot escape. The mantle. Above the core sits the mantle, more than 2,900 kilometers thick, by far the largest part of the planet by volume. Today it is solid rock, though it flows very slowly over geological time. Back then it was molten. And here is where Earth's internal heat actually comes from. Some is leftover heat from formation and from the core still slowly solidifying. But a huge portion comes from radioactive decay, uranium, thorium, and potassium sitting in the mantle, decaying atom by atom, releasing heat continuously. Earth is, in part, a nuclear-heated planet. Those atoms were forged in supernovae before the sun existed, and they are still keeping our world warm from the inside. The crust. The crust is the thin outer shell, the only part any of us will ever touch. Its most abundant element by mass is oxygen, at roughly 46%. Not iron, not silicon. Oxygen locked into minerals. The rocks tell the story of their own formation. Granite and basalt are igneous, cooled directly from magma. Marble and slate are metamorphic, rocks that were buried, squeezed, and heated until their structure transformed, which is why they are found in deeper layers. Push them further, and they melt back into magma entirely. And at the very top sit sedimentary rocks like sandstone, built from broken pieces of older rock, ground down by wind, water, and ice. Even coal belongs to this family. And a note for anyone who was taught this in school: crust, mantle, core is a simplification. Physically, geologists divide Earth into 5 layers: the lithosphere, the asthenosphere, the mesospheric mantle, the outer core, and the inner core. The lithosphere is the rigid outer shell, and it is broken into tectonic plates. Where those plates meet, we get volcanoes. Where they grind past each other, we get earthquakes. Every mountain range on this planet exists because of that fracturing. Below it, the asthenosphere is weak and slowly flowing. The word comes from the Greek for weak, and it acts as the lubricating layer the plates ride on. No asthenosphere, no plate tectonics. Deeper still, the pressure reshapes minerals themselves. Olivine, peridotite, ringwoodite, high-pressure minerals that can only form far below the surface. Which raises a question: if they only form deep in the mantle, and we cannot drill anywhere near that deep, how have we ever held one? We didn't go and get them. Earth sent them up. Volcanic eruptions carry mantle material to the surface, and meteorite impacts hit hard enough to generate the same crushing pressures for an instant, creating those minerals right there in the ground. Now, the outer core. Liquid iron, incredibly hot under enormous pressure, and constantly churning as heat escapes from below. Iron conducts electricity. Move a conductor like that in vast circulating currents, and you generate electric currents. Generate electric currents on that scale, and you generate a magnetic field. Earth has a dynamo running inside it, and the field it produces extends far out into space, wrapping the entire planet. This is not a small detail. This may be one of the single most important reasons life survived here. Because the sun does not only send light, it sends a constant stream of charged particles, the solar wind, and periodically it throws out violent bursts of radiation. Charged particles like these will strip an atmosphere away over time, molecule by molecule, and they will damage living tissue directly. Earth's magnetic field deflects them. It catches the charged particles and redirects them around the planet and toward the poles, which, as a side effect, is why we have auroras. Those green and violet curtains over the Arctic are the visible evidence of your planet defending itself. Mars is the cautionary example. It almost certainly had liquid water and a thicker atmosphere long ago. But Mars is smaller, it cooled faster, its core solidified, and its dynamo shut down. Without a global magnetic field, the solar wind slowly stripped the Martian atmosphere away. The water froze or escaped. What is left is a cold, thin, dry world. Same solar system, same star, different outcome. Largely because one planet kept its dynamo running and the other did not. And that dynamo depends on the outer core staying liquid. As Earth slowly cools, the inner core keeps growing, roughly a millimeter a year, as liquid iron freezes onto it. That is extraordinarily slow. But it means the shield is not permanent. It is running on a very long clock. There is one thing left unexplained. Look up on a clear night, and it is impossible to miss. The moon. Our moon is strange. It is unusually large compared to its planet, bigger relative to Earth than almost any other moon in the solar system relative to its world. So where did it come from? Scientists proposed 3 ideas, and all 3 failed. The capture theory. The moon formed elsewhere, wandered close, and was captured by Earth's gravity. The problem? Capturing an object that large is extremely difficult, and the chemistry of moon rock is far too similar to Earth's for it to have formed somewhere else. The co-formation theory. Earth and moon formed side by side out of the same material at the same time. The problem? Then their compositions should match almost exactly, and they don't. Earth has a large iron core. The moon barely has one. The fission theory. The early Earth spun so fast that a chunk flew off. The problem? No plausible mechanism spins a planet fast enough to do that. So what actually happened? About 4.5 billion years ago, while Earth was still young and still molten, there was another protoplanet sharing this part of the solar system, roughly the size of Mars. We call it Theia, named after the Greek Titan, who was the mother of the moon. Theia's orbit and Earth's orbit were not stable. Around 100 million years after the solar system formed, they met. Two molten worlds collided. The cores of both planets, dense iron and nickel, merged and sank into one. Theia's metal became part of Earth's core. That is why Earth's core makes up roughly 30% of its mass. But the outer layers, the lighter mantle rock of both bodies, were flung out into space. Vaporized and molten debris formed a glowing ring around the shattered Earth. And then gravity did what gravity always does. That ring accreted, the same process that built the planets. And out of the wreckage, the moon formed. Which explains the mystery. The moon's iron core makes up only around 1.6 to 1.8% of its mass, compared to Earth's 30%. The moon is metal poor because it was made almost entirely from mantle material. The metal stayed here, and we can check this. When the Apollo missions brought lunar samples back to Earth, geologists analyzed them and found something remarkable. The basaltic rocks from the moon closely resemble Earth's, and the oxygen isotope ratios, which act like a chemical fingerprint, differing measurably from one part of the solar system to another, match Earth's almost exactly. The moon is not a visitor. The moon is family. So, of the three rejected theories, fission was closest to the truth. The moon really is made of Earth material. It just did not spin off gently. It was knocked out of us. And here's the part that should genuinely unsettle you. That catastrophe is one of the reasons you are alive. The impact knocked Earth's axis over. Our planet now spins tilted at about 23.5 degrees. And that tilt is what gives us seasons. Because as Earth orbits the sun, each hemisphere leans toward it and then away from it, spreading heat around the planet through the year. Without it, climate zones would be far more extreme and locked in place, and adapting to them would have been far harder for life. And the moon gave us tides. Its gravity pulls the oceans into bulges, and as Earth rotates beneath them, coastlines flood and drain twice a day. Those tidal zones, wet, then dry, then wet again, are exactly the kind of environment that pushes organisms to tolerate both. Many biologists think that rhythm helped drive life's move from ocean to land. The moon also stabilizes Earth's tilt over long timescales, keeping our climate from wobbling chaotically. A catastrophic collision gave us our seasons, our tides, and our climate stability. 4 billion years ago, the Hadean ends and the Archean eon begins. The name comes from the Greek arche, meaning beginning. Because this is where Earth starts becoming Earth. The bombardment eased, the layers had separated, a permanent crust formed and held, and volcanoes, enormous numbers of them, erupted continuously, venting gases from the interior: water vapor, carbon dioxide, methane, ammonia, nitrogen. That was our first real atmosphere, and it would have killed you in minutes. There was essentially no free oxygen in it at all, but it did something crucial. It was thick, and it held water vapor. And as Earth continued cooling, that vapor finally reached the point where it could condense and stay condensed. It began to rain, and it did not stop for millions of years. Rain filling the low ground, rain pooling, spreading, joining. Water that had arrived on comets and asteroids, water that had been locked in rock, water that had been thrown into the sky by impacts. All of it finally settling. The oceans formed, and the oceans changed everything. Liquid water absorbed vast amounts of carbon dioxide out of the atmosphere, pulling down the greenhouse effect and moderating the temperature. It gave chemistry somewhere to happen, a place where molecules could meet, dissolve, concentrate, and react over and over for hundreds of millions of years. And somewhere in that water, at some point we still cannot pinpoint, chemistry became biology. Something began copying itself. That relationship between the ocean and the atmosphere never ended, by the way. Even today, the oceans absorb a very large share of the carbon dioxide human activity releases. People usually credit forests and forest matter, but the ocean does the heavier lifting, and that capacity is not unlimited. The more carbon the ocean absorbs, the more acidic it becomes, and the less it can take. The system that made this planet habitable is the same system we are currently testing. So step back and look at the whole chain. A star had to die at the right moment, in the right place, to trigger a cloud that would otherwise have drifted forever. Earth had to form at the right distance from the sun, close enough for liquid water, far enough not to boil away like Venus. It had to be the right size, massive enough for gravity to hold an atmosphere, not so massive that it captured a crushing envelope of hydrogen. It needed a molten iron core to run a dynamo and shield the surface from the solar wind. The shield Mars lost. It needed the right amount of volcanic activity, giving the right greenhouse effect. Too much and we become Venus, a runaway furnace at 460 degrees. Too little and we become Mars, frozen, thin-aired, dry. And it needed a collision with a Mars-sized world at exactly the right angle to produce a large moon, a stable tilt, seasons, and tides. Change any one of those and this video does not exist. Neither do you. I don't say that to make it sound mystical. Physics does not care about us, and given enough planets, unlikely combinations will occur somewhere. But it does mean something practical. We are living on the outcome of 4.5 billion years of dust, fire, collision, cooling, and chemistry. A chain of events we did nothing to earn and cannot repeat. Every mountain, every ocean, every breath of oxygen is the end product of a process that started with a dying star and a cloud of dust in the dark. We are the only place we have ever found where that process produced something that could look back and understand it. That is worth protecting. If you want to know what happened next, how that first self-copying molecule became bacteria, fish, forests, dinosaurs, and eventually you, that story is on this channel too. Thank you for watching. I'll see you in the next one.